Okay, some examples of situations or demonstrating challenges where CFD can help address. For example, this to understand how the fire interacts with their physical surroundings. So now I will show an animation from a CFD simulation of gas jet fire in a congested process facility. So we have a gas release at a horizontal gas release at the lower part of the facility coming from a high pressure vessel. So we have high velocity jet in the horizontal direction. But this jet will now, due to the congestion, quickly impinge on some of the geometry. So the momentum of the jet will be broken, and instead of, so this, within a quite short distance, this horizontal jet will transfer into a buoyant plume, which rises up inside the process facility, so that you see that even if your leak point is quite at a low elevation, horizontal release, you will have a large flame with high temperatures, high heat loads, high up in your facility. So you get a very good picture of what region of your facility which will be exposed to high heat levels for different scenarios. So continuing with another fire simulation, kind of in a similar environment, but now we are at an offshore FPSO. Large pool fire, picture to the left showing a result from the fire simulation. The picture is generated based on the calculated temperatures and smoke volumes. And to the right, a more quantitative result from the same simulation, showing the heat load footprint directly to the topside structure. So you can get a very detailed picture of the heat loads to the various parts of the structure, including shielding effects and things like that. So you can see how large part of your structure is exposed to actual critical heat loads. Continuing with explosions, again from an FPSO, an explosion simulation. To the left, you see some contours of overpressures during the explosion. And to the right, this same type of footprint on the topside structure, now showing the overpressure, including drag force on the different members of the topside structure. Okay, the next, I have another animation, again showing a release. Now we are looking at an LNG tanker, looking at a release during a loading situation. So, and there's an accidental release of LNG from this jetty system, and you see the LNG now is released as droplets, as the system is pressurized. So this cone is representing those LNG droplets, and you will see white gas, which is the evaporated LNG. And this evaporated LNG will be low temperature, so it's heavier than air. It spreads out over the tanker deck. And in this simulation, it eventually finds an ignition point. So it's ignited, and you will see the fire will burn back towards the release source, and we will end up with the steady state jet fire as the release is steady state 10 kilos per second in this situation. But this animation also demonstrates how you can include, in a way, a chain of events following a release into one single CFD simulation. So here the release is specified, and then some ignition points are specified, so that when the burnable mixture of air and gas reaches that ignition point, then it is ignited, and everything that goes on before and after that is handled by the models, the CFD model. Okay. And then one result one could take out again is then typically the heat flux during the fire to the process equipment on that tanker deck. Another example with a fire, now with more focus on the heat loads to structures and objects. In this situation, the heat loads from a fire simulation has been put into another tool to look at the support structure of this vessel and check the integrity of that support structure. So it's the results from the CFD simulation is fed into a structural response tool to get a detailed calculation of the temperature development and also the actual structural response of that support structure. So will it keep its integrity or will it fail? You have to protect this with a fire protection, for example. So here we can see some buckling as a result. Okay, my last example is from a gas dispersion situation in a terrain, onshore terrain, with some buildings and houses. This is actually again a simulation of an LNG release, and what you see here, these blue contours represent the evaporated LNG, representing a flammable gas cloud, and you can see the development in the terrain from 1 minute after the start of release up to the left, and the same scenario now after 10 minutes, and you can see the development of this low cloud of cold, heavy LNG vapor. So what I will do now is that I will demonstrate the use of one of these CFD tools. I will use this KFX tool, which we will give you more information about after the demonstration. I will just say that it's a tool specifically designed for simulating gas dispersion, fires, and explosions in industrial environments and with large domains. So it's optimized for that type of simulations, and also the user interface is optimized for that. So to make it an efficient workflow for setting up cases. Because, as we indicated earlier, CFD tools can be quite overwhelming, in particular for if you are a new user. There are a lot of things to be specified. One has to generate a computational grid. One has to specify a lot of boundary conditions, inlet conditions, and perhaps also set some model parameters. So what has been done with KFX is that the work process of setting up a case has been we have tried to optimize that by generating kind of a minimalistic user interface, which is shown here. It's called a setup wizard. And here we have put together all the required or necessary information to start the simulation. So the idea is that when the user starts from the top of this panel, specifies all the different fields, and when you have gotten to the bottom, you are ready to start the simulation. And then some parameters will be given typically default values. But it will also be possible for the user after generation of the case to go into the more traditional user interface to tweak the simulation, optimize the simulation by changing some of these default values. But today I will demonstrate this wizard for setting up a case. So the first fields here represent some information about the case. I'll just give it a name, jet fire. I have to select the kind of simulation I'm looking at, a fire or a gas dispersion simulation. The main difference between these two is that when we do a fire simulation, then we will have ignition, so that if there is a burnable mixture of air and gas, it will turn into a fire. We will also base the case on a geometry model, which you can see to the right here. So here we see a 3D model of an offshore installation. So I've selected this geometry model now because it's good for demonstrating purposes. So it's an offshore module, but it could just as well have been a model of an onshore facility. So this model is imported from CAD format, a commercial CAD format, a DGN format, I think. And it's a demonstration model, but it has realistic dimensions, and it has quite a high level of detail. So if I just zoom in a little bit on it, and now I'm using the built-in 3D viewer in KFX. So you'll see how that works as well. So I can zoom into one of the process modules on the top side here. So this looks like separation module, some large vessels separators, and I can navigate into that module. So here I have a large vessel with some connections. There's a pipe connection at the top with a flange. So let's look at a leak from that flange. So I use this 3D viewer and zoom in on that flange, and I can position this yellow focus point to pinpoint my release point, like this. Yeah. Okay, so when I've found my release point, I can go back to this wizard and click this Get Point button to copy the coordinates of that release point into my setup wizard. So together with this yellow focus point, you also see some arrows. A red arrow representing the x-axis in my geometry, the green arrow representing the y-axis, and the blue arrow representing the vertical axis, the z-axis. So I also have to specify a leak direction. So let's have a look at, let's try to set up a horizontal release along the x-axis. That means the jet flow now will quite quickly impinge on some of these structures over here. A pipe rack, I think it is. Maybe it's difficult to see the details, but you get the idea of how this works. So I go back to this wizard and specify a release direction, a horizontal release in the positive x direction. So I enter a directional vector. And the release direction, it doesn't have to be along a coordinate axis. It can be at any angle in the horizontal or vertical plane or combination. I also have to specify something about my release. Or there's conditions within this vessel. So I specify the temperature, the pressure, and I can specify that I want to look at the 5 kilo release flow. And by doing that, KFX will perform an expansion calculation to find the conditions of that release as it comes outside the pressurized system. So it calculates an appropriate release area based on these conditions. I could also instead specify that I want to look at the specific hole diameter, and KFX would calculate the appropriate or the corresponding release flow. Okay, so I said something about the release and the location. I will also have to say something about the composition of my leak. Now we are looking at the gas leak. So I can specify any composition of hydrocarbons and also some typical inert species I can include. Now I'll use a mixture of 80% methane and 20% propane. Yeah, so now we have set up actually a jet release. You see also that there are some other tabs here. So if we instead had the liquid release, we could set up a liquid pool or a liquid release location. I also have to say something about the boundary conditions. So let me now zoom out a little bit from our process module. So, and if I now navigate here, looking at now my geometry from the top, looking down at it, still this coordinate axis show the release point. So we'll have a release in the positive x-axis towards the right. So, for example, I could set up the wind from the bottom of the window towards the top. So we will have the wind direction in a cross direction compared to the release direction. And I specified the wind direction as giving angle from north. And from these modules, or in this system, platform north is towards the top of the screen. So I want wind from the bottom of the screen, meaning wind from the south. I can use this slider, or I can enter the angle from north in 180 degrees. I also have to specify a wind speed. And here I've specified a reference wind speed of 10 meters per second. That's a reference wind speed at an elevation of 10 meters. And what KFX will do when we start the simulation is to set up a wind boundary condition representing the atmospheric stability class, which is specified here. This has a default value, which is fine for this type of fire simulation. But we will have a wind profile on the boundary, starting at velocity 0 at the ground or sea level, and then increasing to 10 meters per second at 10 meters, and then increasing further upwards. So I think then we have given all the input data we need. For the release scenario, we have to say also something about our domain and give some input to the automatic grid generation in KFX. And that's done in these last, those bottom fields here. So we will use mostly the default values. I will not go in detail here. Of course, this is described in the manual of KFX. But I can say that for this demo simulation, we will use quite a coarse grid, few grid cells, so it won't take, we don't have to wait too long to generate the model. I've also specified the bottom at the elevation of the sea surface, which in this model is at 465 meters. Typically, when we import these geometry models, CAD models, the sea surface or the ground is not necessarily at 0, it's at some elevation. So what I'll do now is that I will ask KFX to set up a grid based on what we have put in the input in this wizard. Okay, so then in this 3D viewer, we see a representation of the grid calculated by or generated by KFX. So you see it's a Cartesian grid, which is used in this application. And you see there's a fine grid resolution, small grid cells, if we zoom in towards the release location. So if I zoom in again on our release location, we will find the smallest grid cells, and together with the grid, KFX is also showing an arrow indicating the release point and also the release direction. And the reason for concentrating the grid close to the release is that I want to capture the jet scenario, the jet fire scenario. So I want the fine grid resolution here to resolve the large gradients in velocity and temperature, so that I get an accurate representation of the shape and size of my fire and flame, because that will be the most, in a way, important result for example, calculating the heat loads to the surroundings. And then as we zoom out, you see that the grid expands towards the boundaries to make an efficient simulation. So when I'm happy with this, with what I see, I can actually generate the simulation file by clicking this create case files. So what will happen in the background now is that KFX will generate a simulation file or a simulation model. So it will match the grid to the geometry. So each grid cell will have some properties based on what's inside the grid cell. If the grid cell represents just free flow, then it will be a free flow cell so the flow can just pass it. If the one grid cell is blocked by some object, then it will be blocked also in the simulation model. And then we have the situation where parts of the grid cell will be occupied by small objects, and then we will use porosity. So a porosity will be assigned to that grid cell. And the idea is that that porosity should have the same effect on the flow as if we resolved those subgrid objects. So this porosity concept is a method to optimize the simulation, so we can work with, so we don't have to resolve every little object, but still get an accurate result for the flow situation. So now it was the KFX has finished generating the case. Yeah. So we are switching to this another pane, which is used to start the simulation. It is also used to set up what kind of results we want to save. I'll show some results afterwards. For now, I will just start the simulation and make sure we get some output from it. Let's see. So I click the Compute It button to start the simulation. I get some text output from the simulation, and in a little while I will also have some visual output from the simulation. Okay, so again we look at our geometry, our release point, and now you will see the flame developing as the simulation goes on. So we have just started taking small time steps, just simulated for 0.01 seconds, but you will now see the flame developing. In the start, you will see a narrow flame, but then as it impinges on some objects, it will widen out, and we will have a lot of mixing of gas and air, resulting in a wide, bigger flame. So you can see now, quite quickly, we have started from a geometry model, entered the necessary input, and started the simulation, and it's now running on my laptop computer. So while this runs, we would like to look at some results. I've run a simulation in advance, so we have some results, so we don't have to wait. So let's have a look at some results. Again, the same viewer as I used earlier, I'm now using to present some results. So showing what the fire looks like after it has become more or less stabilized, steady state situation after about 10 seconds. It looks like this. The jet fire has now moved out of it extends out of the module, and you see how the wind affects the generation or the smoke plume and the fire, pushing it downwind the rest of the geometry. Okay, so that's just a picture of the flame based on the simulation results. We can also look at some other results. I've taken out some, let's see, some heat loads. Just finding a correct legend. Can cut away some of the. Now looking at the heat load contours inside the process module, you see this is our release point, and between these two vessels now we have high heat loads, while on the back side of this vessel you have lower heat loads due to shielding from the flame due to this vessel. But if I move upwards, you see the heat loads even out, spreads out, and you see also how the heat loads spreads out through the module. I could also quickly look at a different way of presenting, showing a surface now representing 50 kilowatts. Which you can see now is mainly contained inside the module, but this 50 kilowatts contour also extends outside the module a little bit. So, okay. I want to show you one last result from this fire simulation. And that is the heat load footprint. So here I've taken out heat loads directly to the different parts within this module. So you see again our release point close to this from this flange, highest heat loads on this vessel, which is impinged by the flame, and now we are showing a combined heat load of thermal radiation from the flame as well as convective heat flux due to hot combustion gases passing the surfaces. While this vessel closer to the release gets less heat loads because it doesn't experience these combustion gases. Okay, I think that's what we have time for. Just quickly showing you now our simulation, which is still running. Now the fire has developed further. Yeah, a bit difficult to see, but it's starting now to come out of this this module. Still just running for simulating half a second. So just a quick comment on the time schedule here, or the time. This is a steady state release. Typically one would be interested in the steady state results from the flame, and when it has stabilized, that will typically take 15 to 20 seconds. And to get those results, I would have to simulate for a few hours on this computer. Okay, but I think that concludes the demo.